welcome back. Let's continue on with lecture 15 here. Page 4, probably page 4 of 5 or so. I'm only going to do a couple more pages, I think, here. Because we're going to work one more example on shear moment diagrams, and then we're going to move on to chapter 8 and talk about friction. So we've got a beam here, just a simple pin roller, pin on this left end, roller on the right, 2 foot long beam. I'm going to draw it a little longer than maybe we have to, so we get a little more area to show detail. And let's just keep a very simple horizontal surface roller. The complexity here is going to be this. We're going to put on this a triangular distributed load, so a linearly increasing distributed load. Those occur a variety of places in nature. Fluid pressure is an example of that. As I move down in a column of fluid, the pressure increases at a linear rate. That's a linear distributed load at any rate. This is going to go from 0 up to a value of 60 pounds per foot. And again, the span here is going to be a total distance of 2 feet. Okay, now we said in our procedures, first things first, if you can find reactions, find reactions. So we'll do that. So if we find the reactions, hopefully you can find the reactions. Go ahead and pause here. I want to keep this video somewhat short. So go ahead and find the reactions for this one. And by the way, this is A and B. All right, how'd you do with those reactions? Should be able to do some forces, X, Y, and sum of moments and find this one pretty quick. Again, this is a triangular load, so the center is going to be somewhere in here. It's going to be closer to the thick end, further away from the narrow end. It'll be 2/3 of the distance from the 0 point, or 1/3 of the distance from the end point, the thick end over here. So we'll put the area of this triangle is half of 60 times 2, so 60 pounds. Okay, so far so good. You need to be able to do these pretty quickly. Now, this is what I can tell you. With this in mind, knowing these values, knowing I've got a linear distributed load, remember that we know that the shear is the derivative of the moment with respect to x. And the distributed load is going to be the derivative of the shear with respect to x. Now, what do I know here? I've got a linear distributed load. Right? I've got a linear distributed load. So if that means then that the shear is going to be a second order polynomial, because this is a first order polynomial. This is a linear equation here. So the shear is going to be a second order polynomial, and the moment is going to be a third order polynomial, because this is second, so the derivative of the third is going to give you a second order polynomial. So I will have curved surfaces for both of those. So within that in mind, looking at these reactions, I can tell you this, that just if I were to just ballpark this by inspection, if I were to plot my shear, and here's the thing, so if I plot x out here and I plot shear as a function of x on the y. So here's the thing about shear moment diagrams. They always start at 0 and they always end at 0. But the thing is, when I've got a force right here, that's basically going to push the shear up from 0. So right here at x is equal to 0, I'm going to have a force that's going to push my shear up to 20 pounds. And then down over here, I've got a force that's going to push up 40 pounds. But this graph needs to start and stop at 0. So I'm going to start at 0, go up 20, and that means when I get out here to the end, I'm going to be down here at minus 40 pounds, because this reaction right here is going to push it back up to 0. So I know this is what my graph's going to start and end like, because I've got reaction forces here and here pushing the graph up at both points. So at this end, it needs to push up 20 pounds. At this other end, it needs to push up 40 pounds, and it needs to stop at 0, start and stop at 0 at both places. Now again, this is a linear expression, so that means I've got a second order curve for the shear, and it's the same from here to here. It doesn't change. There's no forces. There's nothing else going on from here to here. So what I'm going to have is I'm going to have a curve that's going to be, and it's going to end up being concave down, something like this. That's roughly what my shear is going to look like. There's going to be a point in here where it crosses the 0 axis. And I'm going to need to figure out that value because, remember, then the moment is going to be, the derivative of the moment is going to be the shear. Well, the shear is going to be second order. It's going to be a second order polynomial of some kind because this is a first order polynomial, so this is a second order polynomial. That means the moment is going to be a third order polynomial. If I look at my diagram here, there's no moments, there's no reaction moments, there's no couple moments applied anywhere along here. So unlike here where I've got forces at both ends pushing my shear graph up, there are no moments here like what we saw in the previous graph. There was a reaction moment that pushed the graph down. Here, I've got no moments, no reaction moments, no applied moments. So it's just going to be a concave shape, most likely concave down, and it's going to max wherever that 0 crosses. Again, if I had a couple moment anywhere or a reaction moment, it would push this graph up or down at that point. If the loading changed, right? Now the loading doesn't change. It's the same distributed load all through here. If the loading changed, then I would have maybe a different shape in one region, and then after the next cut, I'd have a different shape. Maybe a curve in one place and a line somewhere else. That happens a lot. But that's not the case here. So your graphs are going to look something like this. Now we got to figure out values here. There's a whole method of what we call generating these by inspection, where you basically apply calculus principles. And you say, which is essentially what I've done here. I said, look, it's a linear distributed load. That means it's a second order curve for the shear, and it's going to be a third order curve for the moment. Right? So let's actually figure those out mathematically. Let's find the values for these. So I've just got one cut in here. It's the same distributed load all the way through. So one cut. I've already found my reactions. So I'm just going to cut the left-hand side of the beam, which, by the way, I'll show you. Maybe we'll show you how to cut the right-hand side, or look at the right-hand side of the beam. Well, let's cut the left-hand side of the beam first. Okay. So I don't have an AX. I have a force here of 20 pounds for AY. I've cut it at an arbitrary distance X. When I've cut it, I've exposed shear and moment. There's no normal or thrust force because there's no X direction forces here to worry about. There is a normal force, it's just 0. So I've got shear and moment. I need to find these as a function of X. And notice that up here, this goes from 0 to 60. But this is not 60. All right, that's not 60. You're going to have an equation here of basically y is equal to mx plus b. It's a linear equation. Right? So m, of course, is going to be your rise over run. M is going to be your rise over run. So if you look over here, this is rising a distance of 60 pound per foot. And that's occurring over a distance of 2 foot. So your M is going to be 30 pound per foot squared, which I'm not going to worry about the units. Okay? Let's just worry about the numbers. M is going to be 30. B is your y-intercept. A little bit of review of algebra today. Remember, I told you guys last time, if you ever talk to a high school student, they're like, when am I ever going to use this algebra stuff? Tell them, oh, if you only knew. B is your y-intercept. Where does this guy, if I'm saying this is my y-axis, right, and it's increasing as we go out here at a rate of 30 as we go along here, and what is an intercept here? Well, it's, in this case, its intercept is 0. You're starting basically at 0. This is y, this is x, and we're saying we're starting right there at the origin. Your b-intercept is 0. So your expression right here is going to be 30x. That is the expression for this line. And if you look at the whole thing, if it's 30 times x, well, if x is 2, 30 times 2 gives me 60. That's what we're looking at there. So the expression for this line here, that is your distributed load, is 30 times x. Okay. So if that's what I've got then, sum of forces in the y direction equal to 0. I've got 20 pounds going up minus my shear, and also minus the area of this triangle. Minus the area of the triangle. Well, the triangle, the height right here is just going to be 30 times x. And its width is going to be x. So at a distance x, its height is 30 times x. So this is the distributed load. Or actually, that would be the area if it's square, but it's not square, it's a triangle. So we need half of that area. We're looking for the area of this triangle to find the force. The area of this triangle is going to be, this height at distance x is 30x. The width is x, and the area of the triangle is half of the height times the width. So this is the quantity for that value there. Okay, the area of the triangle. So my shear then is going to equal 20 pounds minus 15x squared. Right, and if you like, let's just factor the pounds out. Let's not worry about the units. Let's just say the whole thing's in pounds. Not 200, 20. Okay, 20 minus 15x squared. That's our shear force as a function of x. Now, let's do sum of moments about point A. Set that equal to 0. And then that's going to be, so I've got my couple moment there, my bending moment, M, minus my shear force multiplied by x, because I got shear here out at a distance x. So that's going to cause a moment. And then also causing a negative moment, I've got this triangular force here causing a clockwise or negative moment. So the magnitude of the force is going to be 30x times x divided by 2. We did this last time. Remember, that's the force. And then I need to find the location of it. Well, the location of it is going to be 2/3 of the distance from here to here, or 1/3 of the distance from here to here. Well, it's probably easier to measure this. 2/3 of this distance, x. So that's where this is going to get applied, is 2/3 of the distance x. This is force. This is our moment arm. And I need to do some algebra here. All right, so I'm going to plug this in. We'll just say 0 is equal to m minus, I'm going to plug in 20 minus 15x squared. Again, I'm not going to worry about the units. We got enough going on here. The units are going to work out in this case. Minus, then what we got here, this is 15 divided by 3 is 5. The 2's go away. So 30 divided by 3 is 10, and the 2's cancel out. So 10 x cubed. And I need to distribute this x here. So this is m minus 20x. This is minus 15x cubed. So it's going to be plus 15x cubed. And then minus 10x cubed. Is that right? Yeah. So the moment equation, moment is a function of x, I'm going to add all this stuff to the 0 side. So it's going to flip the signs on everything. It's going to be 20x. And this is going to be minus 5x cubed. Okay. Now, a good check here is I've got the expression for moment. Remember, shear is the derivative of moment. I've got my moment equation here. If I take this derivative with respect to x, I should get this expression. So far, so good. If I take the derivative of this expression, because the derivative of this expression should give me the distributed load, if I take the derivative of this expression, I should get 30x. Now there is a sign here. I haven't mentioned this yet. There is a sign here. The distributed load should be the negative of the derivative of the shear. I think that's mentioned in the text. I apologize, I haven't mentioned it before now. But that's what we get here. If I take the derivative of this function, I'll get minus 30x squared, which is what I get up here for my distributed load, at least the negative of it. So far, so good. Now I just need to graph these two equations. And so if I graph these two equations, by the way, remember last time we said, well, plug in your endpoints. I've got endpoints of 0 and 2, so if I plug in 0 for my shear here, what do I get? I get 20. And if I plug in 2 for my shear here, so if I plug in 2 right there, what do I get? I get 4. 4 times 15 is minus 60, so 20 minus 60 is minus 40. That should look familiar. Okay, all right, let's do my moment equation down here. So if I do moment, the limits on my moment equation, well, at x is equal to 0, I should get 0. And if I do moment where x is equal to 2, let's see, if I plug in 2 here, 2 cubed is 2 times 2 is 4, what times 2 more is 8. 8 times 5 is 40, so I've got minus 40 here. 20 times 2 is 40, so I got 40 minus 40, that's 0, which is what we want, at least according, if you believe me earlier, that makes sense. Shear starts at 20, goes down to 40, and moment starts and ends at 0. So far, so good. Okay, let's put some things in here, right? So if I'm to plot this guy out, so if I plot my shear here, x, shear is a function of x, it's going to go up to 20, it's going to go down to minus 40, we're going to start here, so we're going to go up from 0 up to that point, and then out here at the very end, I've got this reaction out here at the very end that needs to be applied to take it back up to 0 from minus 40. And I know I've got a curve in between here. Now, what might be good, because I kind of need to know where is this, it's going to go from here to here, so where is it going to be 0? Well, what I can do is I can come back over here and say, well, you know what is, when I have 0 is equal to 20 minus 15x squared, solve for that real quick. Pause here and solve for that. What is, if I have 0 is equal to 20 minus 15x squared, what is x going to make? All right, so we've got here x is equal to 1.155 is where you get a 0, basically. So I've got an x in here, so if I'm not really keeping track of my scale too good, but somewhere just a little more than half right in here. If you've done a good job here, which I have not, and kept your scale up, you'll be able to figure out just a little more than halfway across, 1.15, 1.115. Should look something like that. And so what we'll want to do then, remember, we said last time, when I first introduced this, I said you should have something like this, and right where it crosses 0 is where your max moment's going to occur. So I need to figure out, what is this max moment? Well, that's going to be where I plug in this x value into my moment equation. So if I find moment at 1.11, or so 1.155, plug in 1.155 in for x here. So that is 20 times 1.55, and then subtract from that 5 times 1.155 to the third power. I get a value there. Can't see I've got some glare there. I'm double checking my value against what I've got in my notes. I've got a value there of 15.4, basically. And the units there are going to be pound-feet. So that's going to be my max moment. So if I draw my moment equation, or my moment diagram here, x, moment of x, I've got a value here of 15.4 pound-feet is going to occur here in line with that 0. I'm going to start at 0, so I've got just a curve. Now if you want to make a more accurate curve, you could start, calculate what the moment is from this equation. You could plug in 0.5 into this equation and come out here at 0.5 and plot a point, and plug in 1 into this equation, right? If I plug in 1 here, what am I going to get? I'm going to get 1 minus 5, I'm going to get 15. So just under this, and right here at 1, I'd have another point. And I could do the same. I could go 1.5 and I could plot another point. I'm perfectly okay if you just say, you know what, Steve, if I look at this, it is a third order curve. It's a curved expression. It's a third order polynomial. It is concave down because of this negative sign here. So if I take the second derivative, I'll get a negative value. It's a concave down shape across the entire span. It's going to go from this max value down to 0 with a curve, and it's going to go from this max value down to 0 to the other way with a curve. Again, if you want a more accurate shape, plot some points. But I am perfectly fine. Go ahead and label your max moment. 15.4 pound-feet at x equal to 1.155 feet. And that is sufficient. All right, we're going to stop there, and we're going to move on to friction from here. Chapter 8 for us.